Tomas Arias is going to tell us about density functional theory and what it can do for us.
Very good. So thank you. It's a great pleasure to be speaking with you all this morning. So as Jim said, I'm going to try to make this a pedagogical talk. What I really want to do is to get across a sense to you all of the kind of capabilities that you have at your disposal in the center as you face material problems as you try to accomplish the center's goals and objectives. You know, in particular, we know that in the SRF cavity group and in the photocathode group, we face a lot of obvious materials questions. I don't know yet whether or not materials issues come up in beam dynamics and storage, but you know, there's properties of magnets and whatnot. So what I hope to do to accomplish is just to put a bee in everyone's bonnet that there are these capabilities out here, and I'm sort of advertising for my group and Richard's group and Jim's group to a certain extent. And if you have an idea of something that we might be able to help you with, please come talk to me, come talk to my students Kevin or Nathan. So the outline of the talk then is going to be, first, I'm going to give you some overview and context of materials theory sort of writ large so that you can appreciate the types of capabilities we have at our fingertips. Some of these are not what are called ab initio methods. I'll describe those in more detail in the following section, but they give you a sense of the kinds of things that we can do. Then I will go on to describe to you what I actually mean by the ab initio approach and why this is such a really powerful method for addressing materials questions. And then I'll give you a sense really of how it works so you can get a sense of what types of problems we can address. I'll describe to you its basic inputs and outputs, and then finally we'll move on to some example applications. Now there's a good number of examples already through my students and also Richard's students of ab initio applications that have already helped the center. And I don't want to step on Kevin's toes or Nathan's toes. I would just refer you to their posters to see those applications. I'll show you some other applications here that give you an idea of the breadth of the kind of things we can do. So let's imagine we're trying to deal with some type of a complex structure that we're trying to design. You know, it might be a superconducting RF cavity. It might be a photocathode, or it might be, say, a cathedral, right? So one way we can think of addressing the materials issues here is to do something that, of course, always drives the philosophers crazy, right? We could take a reductionist approach, and we could say, well, the cathedral is really nothing other than a large collection of nuclei and electrons. But you're really not going to get very far directly with that type of an approach. But in some sense, it actually isn't too far off, because if you take a view of your cathedral, you can think of the materials that can constitute it as some sort of continuum materials, and you can model them with finite element modeling techniques and treat them as a continuum. But if you do that and take a chunk, though, of the material and put it in one of these electron microscopes that David was talking about, very quickly you will realize you're not actually looking at a continuum. You will see at various levels of resolution, you'll first begin to notice the material typically consists of a series of crystalline-type grains, typically, right, which have these planar defects between them, these grain boundaries. And if you zoom in further with the microscope, you'll begin to notice that within the grains, there are these other extended defects. Now they are one-dimensional defects, these dislocations. If you look in even more deeply, you begin to realize that, well, the behavior of these dislocations depend upon the motion of certain atoms in what is known as the dislocation core, and likewise for the grain boundaries. And also, as you begin to zoom in, you begin to realize that there are other types of point defects in the system, right? You've got vacancies, you have impurities, so you might decide, okay, I want to study the system at the level of these atoms, but of course, as we know, the atoms themselves, their behaviors are controlled by the underlying electrons and nuclei that make up the system, and then you can begin to wonder whether or not this type of decomposition to lower and lower levels really could go on in an infinite regress or not. That's where the philosophers come in, and that's where you high energy folks are coming in, trying to explore how far down we can push this. But fortunately, for materials theory, there's a natural terminator to this sequence, and that is at the level of the electrons and nuclei. It turns out to a very high accuracy, you know, to much less than 1%. Whatever materials property might be of interest to you does not depend upon what is going on inside the nucleus. You do not need to know what the quarks and gluons and all that lovely stuff that these accelerators are built to study are doing. You can pretty much treat the nucleus as a point charge of mass and calculate to very high precision whatever basic materials property might be of interest to you. That's a tiny bit overstated, but not very much overstated. So then we really could begin with a description in terms of electrons and nuclei, but if we really want to understand our overall structure, well, that's going to be very difficult if you think we're going to model every single electron in the structure. So what we can do is sort of a systematic climb back up these different scales by coarse graining out in an adiabatic fashion the degrees of freedom that become less relevant as we go up to higher and higher scales. So for example, if I'm dealing with the electrons and nuclei, as you know, the electrons are very light, they tend to whiz around very quickly and adjust to the nuclear positions. So you might begin to think, well, I can really just treat this system in terms of the nuclear degrees of freedom. Where are the nuclei? And what you're building up then is a description of the system in terms of its atomic behaviors. And so there are methods that don't go all the way down to the electronic structure, not these so-called ab initio methods, but methods that deal with atoms as individual units. Sometimes these are called molecular dynamics techniques or interatomic potential models. They have their uses. They aren't quite ab initio, but nonetheless, they are a fairly good description when you can pull them off. It's approximate, but you get a pretty good idea of what's going on. Likewise, as you go up to the next level, you begin to realize that in a natural material, almost all of the atoms are sitting in nearly perfect, almost perfect crystalline environments. It's only relatively few atoms that are experiencing anything different than sort of the normal crystal. And those are the atoms that make up the cores of these dislocations and that make up these grain boundaries. So there are ways then you can focus your attention on those imperfections in the crystal. There are what are called defect dynamics simulations. And I point out that our group has some experience with these. Jim's group has done a lot with dislocation dynamics. So we have a lot of these capabilities throughout the center. As you move up from these kind of defect dynamics of the grain boundaries and the dislocations, you begin to reach a point where you are once again treating your system as a continuum, and then you can do finite element type methods to model your overall structure. So we really have representation of all of these capabilities throughout the center, but what I wanted to focus on today are these electronic structure approaches, these ab initio approaches, because there's something a little bit different about them that makes them special. So what makes the ab initio approach special is it's really that you're following a certain philosophy. And what this philosophy involves is the following idea, right? Our goal, the spirit is we really want to try to make a good stab at the following. We want to predict materials phenomena, but in a special way. We want to do it to very high accuracy, to within just a few percent. We also want to do it completely theoretically, without any experimental input whatsoever. And that's a very key point. Then also we would like to do it again by going down to the best type of knowledge we have that humanity has developed so far of the behavior of nature using our knowledge of fundamental physics. And when we follow this type of philosophy, what you end up with is a very powerful approach. First, you're able to then make high confidence predictions of material-specific parameters. These are going to be real predictions because we have not brought in any empirical input into our calculations. And we're doing them at high accuracy, which allows us to distinguish how one material versus a closely related material, how they will behave, so that then we can make material-specific suggestions for how you can optimize your devices. The second thing that we get out of this is a good way to look at what we're doing here. Because we're not bringing in empirical input, what you have really stands as an independent channel of information apart from experiments. And then we have two different independent channels. And as a result of that, what we have is really amounts to, and this is the best way to think of these, you can think of the calculations we do really as a super high resolution probe, where you know exactly where all the electrons and atoms are, even maybe higher resolution than David's microscope, right? And also we can carry out extremely highly controlled experiments, because after all, we're doing this in the computer. We can put every atom exactly where we want it. We can calculate how it will behave and understand its properties from there.
So purely numerical, you don't have any analytical or some input so they make it numerical calculations easier or simpler?
Oh, yes, certainly we do. We may do things so that we can carry out the calculations. My main point is there's no experimental input into the calculations. Now, of course, I've got David smiling over there because he knows, well, real life is not what I can put into my computer, right? So there's an art to this, right? It's impractical in general to include all of the details that come up in an experiment. We will always have to do, right, the experiments, but still we can gain tremendous insight. For instance, if I was trying to understand some big, complicated catalytic reaction on some metal surface, with a little thought I might realize, oh, what's important in this reaction is the transport of protons across the surface, or something like that. Once I come to that realization, then I can perform this super highly controlled experiment and study one of these protons diffusing across that surface. So there's an art and an expertise involved in understanding what it is precisely you should calculate and then how to interpret the results. Very much like a great experimental microscope, right? The art of what David does isn't just these super high resolution microscopic images. The real art is, well, what do you image and how do you interpret the physics that it's trying to teach you? So that's a way you can conceptualize what it is that we can do. So now let's just look a little bit at basic inputs and outputs and then look at some example applications. So coming to some of the questions we've been getting, so the basic description we're using here is at the level of, again, the electrons and the nuclei. So our basic variables are the electron coordinates, lowercase r, as they are distributed across, say, these electron clouds that I'm showing you here in my picture, and the nuclear coordinates, which tell me where the nuclei are, these capital R. Well, now, I was waiting for someone to challenge me on the idea that there's no experimental input, right? This is not some fantasy philosophy here, right? Some Platonic ideal I'm calculating. There is some, yes. So we need certain fundamental constants of nature that are known to very high precision. Coulomb's constant, Planck's constant. We need to know the charge and mass on the electron and the charge and mass on the nuclei that constitute our system. But that's it. Then what we do is we make an honest effort to solve the many-body Schrödinger equation. Now, of course, that's impractical, right? We just can't do the full many-body Schrödinger equation. Now, ab initio, actually, the term comes from the Latin, which means from the beginning, from first principles. That's a different idea from saying there's no approximations. The key is we're not bringing in experimental input, so we have an independent source of information about how material systems behave. But there are certainly approximations we make, right? But we try to make these approximations so that our resulting calculations are good to within a few percent, so that we can really, make meaningful statements. So the types of outputs that we get, then, you can imagine are, well, we'll have access to all of these wave functions. So we have access to the electronic structure. We have access to all the excitation energy, so we can compute the band structures, all types of quantities that you might want to know. Now, one of these quantities, though, has an incredible wealth of information embedded in it, a surprising amount of information, namely this energy, E, that comes out. Because that energy is a function of the nuclear coordinates. So once I know the energy of my system is a function of where my nuclei are, I can extract all kinds of key information. So here's a simple example of some diatomic molecule. Its energy calculated as a function of the distance between its nuclei. This is the binding curve for the molecule. But if you think about the information in here, look what we can do, right? If we look at the minimum, if we go to find the minimum, we can find the equilibrium bond length of the molecule or the lattice constant in density if it happens to be a solid. By looking at the value of the energy at the minimum, that's the binding energy of the molecule or the cohesive energy of the solid. I can compare that from one phase to another. I can build up phase diagrams of different combinations of materials, all of that kind of information. I can also look at the curvatures involved here. Those are going to tell me the spring constant of the molecule, the elastic moduli that I need in these continuum simulations of my cathedral. They also tell me all about the vibrational properties, and we'll look at those in a moment. And then there's other things we can do. It's really amazing. We can get to study diffusion. If I have some impurities here in my system, and I want to study how it diffuses over to some other location, I can simply march that atom along, calculate the energy along the pathway, determine the diffusion barriers, make important statements about the diffusion constants, and estimate them to a reasonable level of accuracy. So I'd like to switch now to look at some examples of what we can do to give you a sense.
One question. You said that the Schrödinger equation approximation is a few percent error.
The way we solve it is.
But is that how it's depending? The error is depending on size that you deal with.
That's why I express it as a percentage. Right? So the percentage is pretty much a fixed percent type error. So if I wanted the energy of a crystal, it really has a certain energy per unit cell of the crystal. Kilojoules per mole type of a thing. So we get that within a few percent.
That depends independent of the size.
Yeah. I mean, more or less, yeah. Yeah, exactly. So let's look at some examples so we can see. So here's an example, something we had done. We looked at magnesium oxide. It's a key mineral in the Earth's crust and outer mantle. And this is just I pretty much carried out the program that I outlined for the molecule. I'm looking here at a comparison of experiment for the lattice constant, the cohesive energy, and the spring constant, or the bulk modulus, against two different levels of approximation we typically use. We usually use this one as much better. What I'd like you mainly to point out is look at the accuracy and how well we were able to predict these properties directly from first principles. So, within a few percent, we can make some powerful statements. Now, it's not just these simple properties, right? I had mentioned vibrational properties. So, for instance, you can calculate the dispersion relation for the speed of sound. So I'm plotting for you here what's known as the phonon spectrum. The frequency of the phonons versus the wave vector in the what's called the Brillouin zone of the crystal. The black lines are the computation, and the open circles are experiments from neutron scattering data. And just look at the richness of what it reproduces and how accurate. Again, a few percent. It constantly blows my mind, really, when you think that we can actually do this type of a thing. Now, we can look at much more subtle, though, elastic properties. Here's a property that's very important when you have defects and how they behave when you're growing a thin film under stress. There's something known as the defect chemical strain tensor. It's how it couples to long-range strain fields. So we were looking at this defect that's near and dear to my heart. It's called the divacancy defect in silicon. It's when you take two atoms, I've colored them in here in gray, and you remove them out of the silicon lattice. And when we did this work, there was this a debate raging in the literature as to how the remaining atoms, these neighboring atoms in red, how they would arrange themselves. And there were two candidate structures. So we calculated how each of those structures would couple to long-range strain fields because they had experimental data. It's kind of a mechanical spectroscopy. So the experimental data for various components of this tensor are given in black, and our calculations for the two competing structures are given in white and gray, and we were very clearly able to distinguish one proposed structure for the defect from the other, and more importantly, notice again the accuracy of how this fairly subtle effect we can calculate directly again from first principles. We can get electronic structure properties, as I had mentioned. Just quickly, here is a band structure for germanium calculated using these types of techniques. And on the right, there's a comparison of this band structure against, I think this is ARPIS data, must be given by the data points. And again, you see the level and type of agreement that we can get. And the beauty is we can do this for materials that have never been made yet. And you can have confidence in these types of predictions. Here's a more subtle, one last thing I want to mention, because you'll see this on some of the posters. So this is how the electrons behave. You all saw how the phonons are behaving. Well, the electrons can emit and absorb phonons and couple to them. My current students do a lot of work on electron-phonon coupling, and you'll see that in Kevin's poster and some on Nathan's poster as well. So we can get a wealth of information. Here's a more subtle electronic effect. This is hyperfine coupling between electron spin and nuclear spin in a C60 molecule doped with nitrogen, which puts an extra spin into the system. And our calculations of this here were in white, and in black were the experiments in white, and black are our calculations. And again, even for this very subtle type of electronic structure effect, we're able to reproduce it again quite accurately. So here's my final example, then I'll wrap up. This is another one of my favorite examples. This is strontium titanate. This is a crystalline material in contact with liquid water, and this is a really amazing material. It's one of these materials, if you put it in a beaker of water and you put it out in the sunshine, it bubbles off gas. Little bubbles start to form in the liquid, and that's actually little bubbles of hydrogen and oxygen. So you can go directly from solar energy to hydrogen fuel conversion with this material. And our collaborators at Cornell were studying the structure of this interface to understand why it's such a good water splitting material. And I wanted to close on this because this is using CHESS, one of our particle accelerators, right? And they had these X-ray scattering data. I was focused on the structure in blue. I don't want to tell you the whole long story underlining it. So we made an attempt to try to predict this structure for them because they were not able to invert this X-ray scattering data to determine the structure. So over here, I'm showing you our calculation from first principles of the structure where the strontium atoms are in gold, the oxygen in red, the titanium in silver, the green are the electron density contours that we're predicting, and up above you'll notice this is the structuring of the liquid water in a statistical sense. We're able to do this as well. So red shows you the distribution of the oxygen nuclei, and the blue, their associated protons in the H2O molecules. And you'll notice there's a very strong layering and structuring of the liquid water to make sure we were able to predict this correctly without any fitting at all. We were able to calculate this X-ray scattering signature, and so our theoretical curve will be in blue. We'll see how well we do, and you find that indeed we go right through all of the experimental error bars. So we were quite clear that we had the right structure and that we're able to really calculate a wide variety of phenomena. So, the shingle's out, the door's open, please knock on our door. We're very eager to help the center with its mission. Yes, ma'am.
So, when you're working on the bigger systems, are you always only selecting one or two things to put into your program to try to follow what's going on? When you're working with buckyballs, like how big of a system are you actually looking at?
So it depends on the system and what's called for, of course. But we can do, typically on like a little home brew cluster that we have down in the basement, we can do several hundred atoms. You can do larger collections, thousands or tens of thousands if you run on a big supercomputer. So we can build systems that are very large and have a lot going on inside of them. Yeah?
Okay, so then, what do you, I guess, when you're working with the more complex systems, what about the way you're modeling your program or your code or your setup makes your theory so much better than some of the other theory that's coming out? Not necessarily only in this area, but in general. It seems like if you have too small of a system, you're not accurate. If it gets too big, you're sloppy and missing things. So is it just the fact that it's off of the fundamental physics, or what's?
I'm trying to understand precisely your question. So yeah, there are, I don't think I have the pictures that I can access here to show you, give you an example. But there are other methods where, for instance, you just track where the atoms are, say, right? You don't solve Schrodinger's equation. These types of approaches run much more quickly on the computer. You can do millions of atoms this way, right? But when you do that, you're going to sacrifice a certain amount of reliability. So you can use these larger scale simulations, for example, to put in a big droplet of liquid tin on top of niobium and watch them interdiffuse with one another set, right? Now, because these calculations aren't as reliable, you can't really trust quantitatively the results that it's going to tell you. But it might tell you likely what are the likely processes that may be important. Now, once you've identified what the likely important processes are, you can do a much more controlled, detailed calculation, right, at this quantum mechanical level, get accurate quantification of what's going on, and then really determine which are the active processes. So we often play these techniques off of one another.
Okay,
Does that help to address your question?
a little bit. Thank you.
Okay.
I'm not a theory person, so.
Okay. Yeah. Yes.
So now you've done successful calculations, so what's next then? And what are the sort of ultimate goals?
Ultimate goals for what? In what sense, ultimate? Within the center, you mean?
No, within this area of calculations and precision.
Well, it's sort of like any area of science. There's certain frontiers, right, that we're always trying to push those boundaries more forward. So, for instance, something I'm very excited about was this last type of calculation I had shown you, where the traditional method for handling a solid liquid interface within these types of approaches is to actually model explicitly all of the liquid molecules here and do a big, long thermodynamic sampling. But we recently discovered a very powerful technique for removing the need to do all that statistical sampling and to treat in a very special but rigorous way the environment as basically as a very complicated continuum which is much more computationally efficient. So now we're able to solve problems that people take, years of computer running to do, we can do in, weeks or months, right? So that's one particular area. So, I'm not sure that science itself has an actual goal. I was just reading Kuhn's book on scientific revolution, so I got all this stuff in my head, right? So there's different areas of the field that are looking at new things that haven't been calculated ab initio before, right? And some of those involve frontiers. The electron-phonon coupling is something that we've known how to calculate for a long time, but it traditionally had been very arduous. It's sort of like, again, I keep thinking of David's very nice talk where, well, now we have techniques that, can bring us much higher resolution, so to speak, if you will. So we're constantly pushing that forward.
So the materials questions that we run into in day-to-day life in the center for growing niobium 3 tin, for example, you really care about whether the niobium diffuses into the tin or the tin diffuses into the niobium to make niobium 3 tin. You care about grain boundaries, you care about all these things, and some of those questions you need to understand microscopically to get the qualitative picture and the quantitative rates to stick into one of these larger simulations. And some of them, just knowing the qualitative things correctly from density functional can help you think about the problem even as an experimentalist. You don't necessarily need to do the bigger simulations once you find out what's important.
In many ways, it's, again, I like to think of it as it's another type of experiment.
So one of the things that Matthias has found is that a bunch of atoms diffuse in along with nitrogen when you nitrogen dope niobium, which is a big deal for the accelerator people. And Tomas can say, those things shouldn't be diffusing in there. And it's not just carbon atoms coming in and oxygen atoms coming in, something else must be going on. Setting up a puzzle. You trust his calculations well enough to know that they can't be doing what you would naively think they're doing, making a possible sneaky insight that getting at the root of how that stuff is getting in there might help you build better material.
Yeah, stop by their posters, you'll see too. Lots of good stuff. Okay. Good.